So we now know what is adhesion and what are the different mechanisms of adhesion. Like for example, if we have a quick recap, there are different mechanisms of adhesion, including the physical interaction, the chemical interaction, the mechanical interaction, and the diffusion mechanism also is responsible for the adhesion properties. So today we will learn about what are the factors which actually determine or affect the adhesion. So number one we'll start with today is the surface mechanical effects. Now as the name suggests, basically this factor deals with the surface property of the substrate. Now we know that better adhesion of the coating and the adhesives can be easily obtained if the substrate is first roughened before we apply some coating to it. But if the rough surface causes incomplete penetration of coating, then it becomes a disadvantage. So there lies the problem. So if the coating does not completely penetrate into the microscopic pores and the crevices in the surface, then the actual interfacial contact area can be smaller as compared to the geometric area. So basically here what we want to say is we can understand with the help of the diagram. The diagram shows the sample surface which is not even, which is not smooth enough, it is very rough. So ridges and grooves are present. So if we apply the coating upon such surface, okay, the coating will fall into the pores, it will enter the crevices if there is any, and it will fill up all the areas except for those areas which are hard for the coating to penetrate, like the very small one marked with the red circle over here. So that area is slightly curvy and it's the geometry is basically hard for the coating to enter such areas. Even if such areas are more deeper, sometimes we see that this is the simplest one that I have taken over here. We have more complicated areas, the curvy areas wherein the coating is not able to enter, to reach, to penetrate. So those areas actually they do not get the coating layer above them, or let's say the coating is not able to reach those areas. So in these cases what happens, when water permeates through the film, furthermore then there will be areas of contact of water with the uncovered substrate. Uncovered means the substrate surface which is not able to be covered up with the coating due to these tricky roughness areas. So there will be areas of contact of water with the uncovered substrates, which can be a major problem, especially if the coating role is to prevent the corrosion. So the scale of roughness of the surface actually can basically we see that it varies from a very smaller or a tiny one to a bigger area. So it can vary from microscopic to submicroscopic, and the rate of penetration of the liquid into such pores, into such crevices, what is the rate with which the coating will penetrate such areas which are actually ruffled, which are actually pits and grooves and crevices. That situation is similar if we compare it with the penetration of a liquid into a capillary or a micro scale, and it is given by L equals to 2.24 times gamma over eta r cos theta t, where gamma is the surface tension and eta is the viscosity of the coating, theta is the contact angle, t is the time, r is the radius of capillary. Now the rate of penetration, that is L over T, where L is the distance of penetration in centimeters, remember. So the rate of penetration, that is L over T, increases with the increase in surface tension of the coating, as you can see from this equation also, from this expression. So if the surface tension of the coating is increased, it will penetrate at a faster rate into all the grooves and crevices. Now the fastest rate of penetration can be achieved if cos theta is equal to 1, otherwise it will be 0. So if cos theta is equal to 1, that means theta is equal to 0. So if theta is equal to 0, if the contact angle is 0, then we are gonna have the fastest rate of penetration. And this can be only achieved if the surface tension of the liquid is less than that of the surface tension of the substrate or the solid, or in other words, the surface tension of the coating is lesser than that of the substrate, then only cos theta will be 1 and we will have a fastest rate of penetration. That is why we say that the surface tension of the coating should be lesser than that of the substrate over here. So that was the surface mechanical effects, wherein we see that the rate of penetration basically depends on the different factors, out of which the surface tension is the crucial one. The variable which controls the rate of penetration, besides the surface tension, it is the viscosity of the coating. The critical viscosity is that of continuous or the extended phase of the coating, not the bulk viscosity of the coating, including the internal phase of the pigment and the polymer particles, which are very large to participate in this process. So lower the viscosity of the external phase, the more rapid will be the penetration. The second factor which is responsible for the good or the bad adhesion property is the internal stress. Now, the internal stress in coatings, actually, this can lead to the forces inside the coating which counteract adhesion, which do not allow the adhesion to take place. So, internal stress basically results from the inability of the coatings to shrink as they form film on the rigid surface. So when you apply the coating on the rigid surface, if the film or the coating does not shrinks, then it leads to some internal stress in the coating, and the shrinkage occurs when the solvent evaporates from the thermoplastic coating in the early stages. So basically what happens, the shrinkage occurs when the solvent evaporates. When the solvent evaporation takes place from the coating, from the, let's say specifically if we talk about thermoplastic coatings, when the solvent evaporates from such coatings, then the coating or the film starts shrinking in the early stages, due to which the polymers can accommodate the resulting voids by relaxation. So with the film formation, basically the glass transition temperature rises. So when the glass transition temperature rises, the free volume is reduced and it becomes very difficult for the polymer to accommodate those voids which have been created by the evaporation of the solvent. So it becomes fixed in unstable conformations and leads to stress. So when the molecules, they are not able to fill the voids created by the solvent evaporation, that leads to stress inside the coating. In some cases, the stress build up sufficiently that spontaneous delamination occurs. So much amount of stress develops inside the coating that actually the coating starts delaminating. It starts peeling off from the surface. So stress can also result due to volume expansion. Like for example, when the film swell by exposure to humidity or water immersion. So when you dip a substance which has a coating in water, or let's say you pour some water for a longer period of time, then the stress develops in that coating due to the volume expansion. Now in thermosetting coatings, cross-linking occurs, we know it very well, as compared to the thermoplastic. So cross-linking in thermosetting coatings, this leads to formation of covalent bonds between the polymeric chains, which are shorter than the distance between two molecules before they react. So when such reaction occurs at the glass transition temperature of the film, stress formation takes place, due to which the coating undergoes shrinkage. As the cross-linking increases in these thermosetting coatings or the films, the stress also increases. So with the increase in cross-linking, the stress is increasing over here because less time is available for the polymer relaxation. You know it very well that the coating molecules, the polymeric chain or the polymers present in the coating, they also need some time for relaxation, for coming back, or for let's say spreading themselves on the surface. So that's called as polymer relaxation. Like for example, in UV curing of acrylated resins, when we use the free radical polymerization process, it occurs in a fraction of second at ambient temperature. But the high rate of polymerization, together with the relatively large shrinkage, accompanies the polymerization of double bonds, contributing to generally observed poor adhesion of UV cure acrylated resins to the smooth metal surfaces. We'll understand this particular aspect in another way. Let's say we apply some UV cured polymeric coatings, and what coating specifically we are talking about is acrylated resins. So when we apply the UV cured acrylated resins, and the mechanism of polymerization which is being followed here is free radical polymerization. So what happens when the polymerization onsets, the polymeric chains, they link together, and that process, it takes only a fraction of seconds at ambient temperature, at room temperature. What happens if the rate of polymerization is high, then the shrinkage will be happening at a faster pace. Okay, so, or let's say large shrinkage accompanies the polymerization of the double bonds, which actually leads to further poor adhesion properties of the coating, because polymer is not getting the time for relaxation. Now, heating after UV curing relaxes the cross-linked network, and that leads to improved adhesion, because now the polymer is getting the time for relaxation, so they can move on, they can link with other molecules, or they can occupy those void spaces if created and spread themselves evenly. That leads to improved adhesion. This is about the internal stress. So in short, internal stress is created inside the leads to the forces responsible for poor adhesion properties of the coating. So we need to minimize the internal stress of the coating, and there are different reasons why the internal stress is being created. Either the solvent evaporation is taking place at a faster pace, so the polymers are not getting the time to relax and then occupy those vacant spaces created by the solvent. And then we talked about the thermoplastic and the thermosetting coatings, the differences between them, how the shrinkage is happening differently in different cases in these cases. And we also came to know that in some cases the so much of stress builds up in the coating that actually delamination of coating takes place, and hence poor adhesion properties. Okay, so the next factor which determines or affects the adhesion is the wetting. Now, what's wetting? It's a major limiting factor in adhesion. What is a contact angle? A contact angle gives you an indication of how well or how poorly a liquid spreads on the surface. Like for example, suppose you put a drop of the liquid on the surface. So either of the two cases happen. Either it will flow over the surface, or it will just remain as a tiny drop wherever you have placed it on the surface. Spreads or it remains in the droplet form. Basically, that depends on the intermolecular interaction between the solid and the drop that you have placed, and the contact angle between the two surfaces, or let's say the drop and the solid substrate. This gives us information about the wettability of the solid surface. So we say that a coating does not spread spontaneously over a substrate or the surface, so that there is an intermolecular interaction between the substrate and the coating. So there cannot be any interaction, and so the adhesion will be difficult. So if there is no interaction, definitely adhesion will be difficult to achieve. Now, if the measured contact angle is greater than 90 degree, then the solid is said to have poor wetting properties, which means that the liquid will just stay in the droplet form and will not spread on the surface. As you can see in the figure also, less than 90 towards the extreme left first case, it will stay in the drop form. If the theta or the contact angle is greater than 90, then the liquid will spread over the surface, or it will wet the surface wherever it is placed. As you can also see in the inset provided, that if the theta is less than 90, then the liquid is just simply spreading over the surface. It is 0, complete wetting is taking place. It is 20 degrees, excellent wetting is taking place. But once it exceeds 90 degree, Then poor wetting, that means it just remains as a single drop in its own place. So we see that the contact angle has some relation to the wettability or the wetting property of the liquid, of the coating over here. And we see that as the wettability increases, contact angle decreases, or vice versa. If the contact angle is increasing, wettability is decreasing. So we can say that the wettability is inversely proportional to the contact angle. Now there are different factors which actually can affect the contact angle or the wettability of the liquid, of the coating over here. What are those factors? The rough surface. The surface roughness is responsible for the wettability because it will decide the contact angle and hence the wettability. The functional groups which are present on the surface will also be responsible in changing the wettability of the liquid. The impurities present on the surface, they will also hamper the wettability of the liquid. The porosity of the surface and the surface energy, they all have their individual roles in the providing, or let's say preventing, the wettability of the liquid. So generally we see that the solid surfaces, they are not smooth, but they are irregular and they contain defects, voids, or some local deformations. And the Young's equation that we use is suited for the ideal surfaces, which are the smooth and the flat surfaces.